example of the combination of the interference and diffraction pattern. This fringe, bright and dark fringe, is the interference pattern double slit from double slit. From double slit. But anyway, if you notice that we have the bright region here and then it becomes dark, and then again you have the interference pattern here again and the interference pattern here again, and then it becomes dark again. These come from the diffraction. Okay, these come from the diffraction. So when we combine the pattern from the double slit interference pattern and the diffraction pattern, we will have this kind of diffraction, this kind of fringe. Okay, and the intensity of the fringe is just the combination of the density of the double slit, which is the first term. Okay, this is the interference of the double slit, and the second term is the intensity, not interference, but the intensity of the diffraction. So the total intensity is the product of the intensity of the double slit and the diffraction. Okay, don't worry about this formula too much. I just give you to know that we have this kind of relation. But if I want you to do some calculation on this, I will give you the formula because it's too complicated to remember. Okay, but I just give you the combination of these two phenomena. The point is that we can calculate the number of the interference pattern inside the first bright fringe, from the diffraction pattern. This is the first fringe for the diffraction, and inside the detail is the fringe for the double slit interference. And the point is that at this point, the center of the dark fringe, the angle is equal to theta, and we have that a sin theta is equal to lambda, right? A sin theta is equal to lambda is the position of the first dark fringe. And also we have that d sin theta equal to m lambda. It means that if for the same lambda we have the m fringe from the center to the first dark fringe, and this angle theta is the angle for the interference pattern at the center of the dark fringe. So when we divide d sin theta over a sin theta, we will get that d over a is equal to m. This d over a equal to m is the number of interference fringe start from the center point to the center of the first dark fringe. For example, if you look at this figure, we have m here is equal to the 1, 2, 3, 4, 5, and about 6. Okay, at the center at about 6. It means that you have 6 interference pattern in the first diffraction pattern. I mean, from the center point to the first dark fringe from the diffraction pattern, you have 6 fringes of the interference pattern. So this equation is interesting. You can see that if D is much larger than A, you will have a lot of fringe, interference fringe in the first, from the center point to the first dark fringe from the diffraction pattern. In normal situation, in the real experiment, you may have that A is very small. And when A is very small and D is quite large compared to A, you can have a lot of interference fringe from the center point to the first dark fringe. And when you do the experiment, you don't have to worry about this dark fringe because you will have a lot of interference pattern here to study about the interference. Okay, so that is the condition if you want to have a lot of fringe here. Okay. When the light can diffract, they will produce some problem. For example, the diffraction happen every time that you let the light pass to a narrow open or narrow slit. For example, if you look for your eye, you have a hole on your eye, right? When the light pass through your eye, it also produce the diffraction pattern. But it also depend on the size of the slit. So if the size of the slit is quite large, the interference pattern will be large, and you don't have the interference pattern will be small, and you don't have to worry about the effect of the interference pattern. Okay, you have that from the formula, right? A sin theta equal to m lambda, right? So for example, if I take m equal to 1, I will have that A sin theta equal to lambda. So for the light, for the same wavelength lambda, for fixed wavelength lambda, you have that sin theta equal to lambda over A. So it means that if A is quite large compared to the lambda, what is the size of the theta? If A is large, theta will small, right? So it means that the diffraction pattern will be very narrow. But when A is small, the diffraction pattern can be very large. And the problem is that if you have the light from two objects that pass through the narrow slit, like when you look at the microscope, okay, the light have to pass to the eyepiece, which is maybe the small hole, okay, so it will produce the diffraction pattern. And if you look at the two objects here, S1 and S2, and the light from these two objects will produce the diffraction pattern, on the screen. In this case, it's on our eye. And if this diffraction pattern is too large, so it means that the image of these two objects will merge together, and what you see is that you may see as only a single object, but in fact it comes from the different object. Okay, this is a problem for every optical instrument, so you have to worry about this, that when you use the optical instrument, they have to specify the resolution of the instrument, that how large the separation between two objects is needed to that you can resolve these two objects. This is the example. When two light source that is quite far apart, and when the light pass to a hole, these two light source, okay, you have a hole and you have two light source, and this is far apart like this, and once the light is passed through the hole, it produces the diffraction pattern. You can see this is the diffraction pattern. This is the center fringe, and this is the first bright fringe. This is the dark fringe. Okay, and when you make these two objects come closer, the diffraction pattern of these two objects will merge, and it look more like a single object. But for this figure, you may can notice that it may come from a different object. But for the last figure, the light come from two sources,